Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the next few videos, we're going to look at different types of waves, focusing on both sound and light waves. Because of this, it will be a good idea to first have a short introductory video to wave theory in general. In this introductory video, we are going to look at different wave properties, for example, the amplitude, the frequency, and the phase of a wave. I will also split waves into two different categories, transverse and longitudinal waves, depending upon both the direction of vibration of that wave and the direction of its propagation. As I mentioned, the focus of the next few videos will be about physical waves like sound and light. However, wave theory also applies to non-physical waves, for example, wave-like motion. For example, consider the following situation. Let's assume that we have a spring attached to a ceiling as shown here, and we then attach an object such as a ball at the end of that spring. After that ball has been attached, let's call y equal to 0 the position that the center of that ball rests at when it is not moving. Let us then pull down on this object and then let it go. Naturally, this ball-spring system is going to oscillate. It is going to go back and forth from this equilibrium position, from this y is equal to 0 position. This is known as periodic motion. To visualize this motion, let us draw a graph. Let us have the horizontal axis be time, and the vertical axis be this displacement from the equilibrium position, this y value. The motion of this ball would then follow a simple sine wave, as I've shown here. This is why periodic motion such as this also falls into the category of wave theory. Wave properties that I'm about to discuss about physical waves can also be applied to wave graphs such as this. Of course, if I instead wanted to represent a physical wave on a graph, I could instead replace the time axis with horizontal displacement with instead x. If I had x on the x-axis and y on the y-axis and drew a sine wave again, that would represent a physical wave like light or sound. Before describing various properties of this graph, let us make sure that we understand why the graph has the shape that it has. Initially, at time t is equal to 0, the ball is in its equilibrium position. Therefore, at t is equal to 0, y is equal to 0, as I have drawn here. The ball then oscillates between some maximum height above y is equal to 0 and some maximum height below y is equal to 0, passing y is equal to 0 at various instances in time. Therefore, it hopefully makes sense that the resulting motion of this object follows a sine wave pattern. The following properties of such a sine wave are true in general, true for periodic motion as well as physical waves like light and sound. The maximum displacement of this wave from its equilibrium position, in other words its maximum or minimum y value, is known as the amplitude capital A, as I have shown here. This is, if you like, the height of the wave, the distance from the horizontal axis to the maximum height on either side of the x-axis. This wave property, in a sense, quantifies the vertical displacement of a wave. In other words, the height of a wave. However, we would also like a property that quantifies the wave horizontally. A value that tells us how squashed or how spread apart the sine wave is. This quantity is known as the wavelength, and we use the Greek letter lambda to represent it. Wavelength is more precisely defined as the distance between two successive points on a wave. For example, as I have drawn here, it is the distance between two maximum heights, two amplitudes on a wave. These points are in fact known as antinodes. It is the distance between two successive antinodes. It is also the distance between two successive nodes. Nodes are the points at which this curve crosses the t-axis or the horizontal axis. The distance between two successive nodes is equal to the distance between two successive antinodes. In general, in fact, the distance between one point on a wave and its next successive point is constant. That is known as the wavelength. The wavelength is simply equal to the distance between two successive points on a wave. As both wavelength and amplitude have to do with distance, they are naturally measured in meters. Of course, when dealing with a physical wave such as light, a meter is going to be too big of a measure, and we will use prefixes such as nano to represent distances on a smaller scale. These two quantities alone, in a sense, determine the size of the sine wave. Of course, there are other things about this wave we would be interested in. Remember, this particular wave is representing a ball on a spring oscillating between an equilibrium position. Both the amplitude and the wavelength are only telling us about distances from that equilibrium position. However, we would also like to know how often or how fast is that ball oscillating. To do this, we introduce what is known as frequency. Frequency is simply defined as the number of oscillations per unit time. In other words, in this case here, it is in a sense a measure of how often that ball returns to the equilibrium position. Since frequency is number per unit time, and as number really doesn't have any units, it has units of per time, it has units of per second. Again, instead of writing per second all the time, we define a per second as a hertz. Hertz is again per second, and the symbol we use is capital H small z. For example, in this case, if that ball returned to its equilibrium position 5 times in 1 second, then we would say its frequency is 5 Hz. This of course also means that it takes 1 over 5, in other words 0.2 seconds, to go from the equilibrium position back to the equilibrium position, in other words to do 1 cycle. This time is known as the period. The period is simply the inverse of frequency. The period capital T is equal to 1 over f, and it tells us the time it takes for this object in this case to do 1 complete cycle. Now I would instead like to focus in on physical waves, waves that are actually moving through space. As I mentioned at the start of this video, I'm going to break up such physical waves into 2 different categories. The first of these categories is known as transverse waves. A transverse wave is simply a wave that is vibrating at right angles to the direction it is moving. To understand what this means, allow me to draw a physical wave. Again, as I mentioned, a physical wave is represented by simply having the horizontal displacement on the x-axis and the vertical displacement on the y-axis, as I have shown here. As this is an actual physical wave, this wave that I have drawn is also moving. It is moving, for example, to the left or right. However, a transverse wave, as I have stated, is a wave that propagates at right angles to the direction of vibrations. In other words, the direction of wave propagation is perpendicular to the direction of vibration. The direction of vibration is of course vertical in this diagram, and therefore the wave must be moving to the left or right. If this is to be a transverse wave, it must be propagating to the left or right. For such waves, it is also useful to introduce the idea of what is known as the phase. The phase of a wave is simply the offset of that wave from either the origin or another wave. For example, as I have drawn here, this wave passes through the origin. Therefore, we say that its phase is 0 degrees. However, if we draw the exact same wave but shift it slightly to the right, then we have introduced a phase shift. If those waves were overlapping exactly, then we would say that they were in phase. The phase shift would be 0 degrees. If instead the nodes of one wave overlaps with the antinodes of another wave, in other words, the amplitude of one wave overlaps with the other wave at y is equal to 0, then those waves are said to be in antiphase. The phase shift is said to be 180 degrees, as one wave is exactly halfway through the cycle of the other waves. A full cycle is said to be 360 degrees, and therefore antiphase is a phase shift of 180 degrees. Finally, we can also discuss the other type of wave known as a longitudinal wave. As you may have guessed, a longitudinal wave is a wave in which the direction of vibration is parallel to the direction of wave propagation. To visualize this type of wave, allow us to go back to a gas within a container and a piston pushing on that gas as I have drawn here. As that piston moves to the right, it is going to naturally push particles within the air to the right. This will create an area within the container that has air particles closer to each other than in other parts of the container. We can then at a later time push the piston in again, creating another area of compression. Overall, we are going to end up with areas of spread out air particles and areas of air particles closer together. In other words, compression regions and rarefaction regions. What we have in essence created are longitudinal waves. These waves are in a sense vibrating in the horizontal direction as well as propagating in the horizontal direction, therefore satisfying the conditions for a longitudinal wave. As both properties are parallel, you may naively assume that it is not possible to represent such longitudinal waves by sine waves on a graph. However, if we were to plot, for example, distance on the x-axis and density on the y-axis, we would again get a sine wave. This is because the density is still oscillating at different positions within the container. As we shall see in a following video, sound can be considered a longitudinal wave. Sound is simply longitudinal waves or vibrations that travel through the air. On the other hand, light waves are an example of a transverse wave. Light waves propagate perpendicular to the direction of vibration. Let us now very quickly recap this introduction to wave theory that I have presented. The first question is testing our knowledge on various wave properties. It is asking what is the number of seconds per wave cycle better known as? Is it amplitude, period, frequency, or phase? This question can be answered even without knowing the precise definitions of each of these quantities. We are asked to find the quantity that is the number of seconds per wave cycle. A wave cycle, of course, has no units, and therefore the number of seconds per wave cycle is simply going to have units of seconds. Amplitude, if you remember, has to do with the height of the wave. It is therefore a measure of distance and is instead measured in meters. Frequency, if you remember, is measured in hertz, which I defined as a per second. Therefore, it cannot have units of seconds. The phase of a wave has to do with the offset from some reference point like the origin. And as I discussed, it is measured in degrees. This only leaves us with option B, the period, which is indeed the number of seconds per wave cycle. For example, for periodic motion, it is defined as the time it takes for that object to go from its equilibrium position back to its equilibrium position. In other words, the time it takes to do one complete cycle. Therefore, the correct answer is option B. This final question is testing our knowledge on transverse and longitudinal waves. It is asking us which of the following is a type of longitudinal wave: a seismic wave, an electromagnetic wave, a wave on a string, or a water wave. Well, as I mentioned earlier in this video, light is a type of transverse wave, and therefore electromagnetic waves are instead transverse waves. For option C, consider tying one end of a string to a wall and holding the other end in your hand. You can then oscillate that string vertically, creating transverse waves. Therefore, waves on a string are considered transverse waves. If this was instead a spring instead of a string, we could create either transverse or longitudinal waves. We could move our hand up and down, creating transverse waves, or we can push back and forth on that spring, creating pulses, in other words, longitudinal waves. To determine whether a water wave is transverse or longitudinal, we simply have to picture how water waves are created. For example, we can consider dropping a rock into water. Dropping such an object is going to create waves that spread out from that rock. Those waves have an amplitude in the vertical direction, but those waves are moving horizontally outwards. Therefore, the direction of propagation is perpendicular to, or at right angles to, the direction of oscillation. Therefore, these are instead a type of transverse wave. This leaves us with option A, seismic waves. Seismic waves are waves created by a disturbance in the Earth's crust, for example by an earthquake. Such waves can in fact be either transverse or longitudinal. This is because when an earthquake happens, two different types of waves are created: primary or P waves, which are longitudinal, and secondary or S waves, which are transverse. However, as this is the only wave type in these options that can include longitudinal waves, this must be the correct answer. The correct answer is option A. As I stated at the start of this video, the purpose of this video is simply to give you a brief introduction to the idea of wave theory. In the next few videos, we are going to focus in on two types of physical waves, namely light and sound waves. As I also stated, non-physical waves can also be represented by the same properties. For example, an object that is oscillating between an equilibrium position is undergoing periodic motion and can also be represented by a wave in a graph. Both physical and non-physical waves share the same properties. One property is that of wavelength. A wavelength quantifies the size of a wave horizontally. It is a measure of the distance between two successive points on a wave. As it is a measure of distance, it is measured in meters. To quantify a wave vertically, in other words to describe the height of the wave, we instead use the amplitude. The wave amplitude is the height of a wave from the equilibrium position. Again, as it is a measure of distance, it is again measured in meters. The concept of frequency was then introduced, which is simply the number of wavelengths per second. For example, in periodic motion, it is defined as the number of times that object returns to its equilibrium position in 1 second. If it does it 10 times in 1 second, then its frequency is 10 Hertz. The unit of frequency is a Hertz, which is simply a per second. I then introduced the inverse of frequency, which is known as period. As period is the inverse of a per second, it is measured in seconds, and in the case of periodic motion, it is defined as the time it takes for that object to go from its equilibrium position back to its equilibrium position. In other words, the time it takes to do one complete cycle. Wave phase was then discussed, which is simply the offset of a wave from a reference point or from another wave. It is measured in degrees, as it is a measure of the offset from 0 degrees from the reference point. If it is offset by half a wavelength, then the phase shift is 180 degrees. It is said to be in antiphase. If it instead overlaps with the reference wave or reference point, then it is said to be in phase. The phase shift is 0 degrees. Finally, I broke up waves into two different categories, transverse and longitudinal waves. A transverse wave is a wave that propagates perpendicular to the direction of vibration. As I stated in the last question, water waves are a type of transverse wave, but the transverse wave we are most interested in is instead light waves or electromagnetic waves, which will be the focus of a future video. The other type of wave is a longitudinal wave. Longitudinal waves propagate parallel to the direction of vibration. Again, seismic waves are a type of longitudinal wave, but the longitudinal wave we will instead focus on is sound waves. Light waves and sound waves will be the focus of the next few videos. Again, as these are a type of waves, please ensure you are comfortable with this introduction to waves that I've just introduced. Once you feel comfortable with these ideas, please move on to this series of videos about light and sound. As always, I hope these videos have been useful to you, and I shall see you guys in the next one.